The question is, why do we draw shear and bending moment diagram for a beam? In answering this question, let me first list the key steps of structural design in a broader sense. First, we define the problem, which entails defining things like geometry, boundary conditions, materials, and the loading of the structural element that we are interested in designing. And of course, here we are interested in designing a beam. So once we have the problem completely defined, we can go ahead and analyze the problem in order to find first the support reaction, then the deflections, and then the internal forces. So internal forces will depend on the type of structural element. For a beam, the internal forces would include the shear force and the bending moment. Our third major step would be to calculate the stresses due to the internal forces, and then the final step would be to ensure that the stresses due to these internal forces are adequately smaller than the corresponding strengths of the material forming the structural element. So you can see the calculation of the internal forces is a major part of this design procedure. So what we do is we go ahead and design the beam for the maximum shear force and the bending moment that occur on the beam. Since we don't know exactly what the maximum shear force and the bending moment and where exactly those are going to happen, what we do is we try to plot the distribution of the shear force and the bending moment along the length of the beam. Then by looking at this diagram, we will know exactly where the maximum shear force occurs, where the bending moment occurs, and exactly what those values are. So here's an example. We have a cantilever beam fixed at point B and subjected to a point load at point A. The value of the point load is 2 kilonewton, and we have a distributed load from point C to point B. The value of the distributed load is 1.5 kilonewton per meter, right? Here is the shear force diagram for that, and here is the bending moment diagram for that, right? The shear force diagram and the bending moment diagrams are indicated by these red lines, right? So we design the beam that is capable of supporting these shear and bending moment values. So for convenience and for economic reasons, normally we don't use beams with variable cross sections. In other words, we design the beam with a constant cross-section, right? So you want to come up with a cross-section that is capable of supporting the bending moment and the shear force at any point along the beam, right? So what it boils down to is you design the cross-section that is capable of supporting the maximum bending moment and the maximum shear force. So this is the ultimate purpose of the shear force diagrams and the bending moment diagrams. In this particular example, we can see the shear force varies from -2 at point A to -5 at point B, and the bending moment varies from 0 at this point to -11 at point B, right? For this problem, from the shear force and the bending moment diagrams, we see that the absolute value of the maximum shear force is 5 kilonewton, and the maximum bending moment is 11 kilonewton meter, right? And they happen to occur at point B. We will learn that the bending moment Mmax produces a normal stress on this cross-section at point B. Specifically, it produces sigma xx, which is the stress on the x-plane in the x direction. And we will learn that sigma xx is a function of Mmax and some specific sectional properties. And similarly, we will learn that the shear force Vmax produces a shear stress tau xy. As you might recall, tau xy is the shear stress component on the x-plane in the y direction, right? Which is that direction right there, the vertical direction. There is a functional relationship between tau xy and the maximum shear force Vmax and certain specific sectional properties. So this is how we're going to calculate the stresses produced by the shear force and the bending moment. Now you see the use of the shear force and the bending moment diagrams in the design of this particular structural element.